Hey Sridhar,
Hey.
how is Mumbai?
Yeah, fine.
अचानक से कैसे?
No, I was planning a trip for a long time. I thought,
You took a chartered plane or regular or
yeah, I could have done that. I did the next best thing.
deep sanitized plane?
Started plane. Yeah, वही करना चाहिए. You guys have to come up with low cost.
Why should we come up?
You guys are doing smart transportation.
So you got scared in the flights or it was okay?
Pardon?
Seeing so many, you got scared in the flights?
Kind of. I mean, it was still unnerving, but it's okay. But okay, I don't want to brag, but I flew business, so ठीक है.
Oh, okay. कौन सा एयरलाइन जाता है बिजनेस? एयर इंडिया.
Air India, LTC.
Oh, okay. अच्छा अभी LTC ले सकते हैं?
Yeah, you can tell. LTC is always possible. No?
Oh, okay.
LTC is not frozen.
Okay.
How are the other workshops?
Yeah, going well. I attended one RL one today. I think yesterday say today attendance is much lower.
Is it? Okay.
Even in the plenaries.
Oh. Where are you? IIT or Bombay?
Very much in IIT. Professor Nirav.
Hi, Sridhar, you made it.
Yeah. Hey, what happened to our Kritika? She's not well, huh?
Yeah.
COVID, huh?
Yesterday she was not well. I asked her to go back in the morning itself.
But COVID, huh?
I don't know. Yeah, nothing. This is a simple viral.
What do you know? COVID is also simple virus only.
Yeah, then why should we worry?
Uh,
Why should we worry then?
oh, she has to get tested, no?
What is point of spending $400 and putting your name as a statistic? Do you get tested for a common cold? You tell me. Let me ask a simple question. 3 years ago, when I had a dengue, first they gave me a couple of days viral fever.
Yeah, people are joining here. Let us have this discussion
Afterwards.
They can also join in this discussion, no? And we can talk about biological networks later.
There's no section, no? Identifiability and control of pandemics.
Yeah, that's what I told. No, one of the model is a reaction network model. Epidemiological models are reaction networks model with the conservation and everything by the. So we do not need the identifiability is a big issue there also, no?
Okay, so how many you expect in the audience today? Others may the speaker hasn't yet joined. I don't need
Arun.
to tell you who speaker is.
Arun.
Yes.
Arun will join exact time. 2 minutes.
Okay. 4:58 is too early anyways.
Yeah. Arun, it is too early. Arun will join exact time and perfectly when he's supposed to join.
Nirav, ticket खरीदा है? Not yet.
I'll buy. Plan is sure, then I'll buy.
Plan is sure होगा, कुछ नहीं है. मैं अभी कितना minutely हो गया उधर plan without you knowing.
I'll buy ticket tonight from Bangalore to Bangalore.
चुनाव declare हुआ नहीं, लेकिन candidate declare हो गया वैसा है.
Ticket from where?
I'll tell you later on. I'll call you afterward and then.
So Sridhar said he booked business class and went. So you can also book the entire row and go.
I'm not that rich.
Oh, professor.
Yeah.
Anyways.
Just abusing the privileges of professor.
Not abusing. You're using that.
Yeah, all this is recorded. Sridhar, all this is recorded. I can play this on.
Okay, I'm using
selectively. I can play and link
use it. Call it using. Don't say that.
for all the hard work that I've done.
Yeah, for the institute.
Yeah.
For the country, yeah, I can say.
Does the institute think the same?
That's not our job to think that. We are karmane vadikaraste ma phalesu kadachana. In case of Sridhar, he already did karma. He's looking at the fruits of those karma. Anyway, we can start. I think 5 o'clock is
Yeah,
there.
yeah.
So Sridhar, you speak today?
Yeah. Can we start?
Yes, yes. You want me to say some nice things about you?
Would you like?
Okay, you can say, you can introduce Sridhar.
Yeah. Good evening, everyone. Thank you for coming to the second day of tutorial of a priori identifiability of chemical reaction networks. In the lecture 1, we discussed, I have discussed the modeling of the reaction networks. Today, Professor Sridhar Kumar Narasimhan, who is affiliated with Department of Chemical Engineering, as well as Center for Network Systems, Center of Excellence for Network Systems. We call it CENS at IIT Madras, and Robert Bosch Center for Data Science and AI. So and the water network also. So he worked in a quite much in a sensor placement for large networks, as well as input convex optimization formulation for different problems, and of course with in collaboration with me, we are working on identification of reaction networks from the data, as well as performing the experiment to validate some of those theory which we developed. So today he's going to talk about a differential algebra approach for systems identification and its application to chemical reaction networks, and some issues associated with those techniques. So over to Sridhar. Thank you, Sridhar. Can you start your presentation?
Hello, good evening. Thanks for the introduction, Ram and Meera. And welcome to a few brave people who have joined today. Let me start sharing my screen before I. Okay, to full screen. Okay, so I think the screen is visible, and I hope I'm clear and loud.
Sridhar, your screen is not in full screen mode. I think you.
Oh, I've. How about now?
I can't. No.
Let me try again. I think is it clear now?
Sridhar.
Is it better? Yeah, can you see the screen now? Full screen?
Yeah, I can see now.
Yes, it is good.
Thanks, sorry for the couple of minutes for the brief disruption. As Meera mentioned, I'm with the Department of Chemical Engineering at IIT Madras, and we are also with. I see that the Center for Network Systems is really heavily represented in these workshops at ICC. Two of my other colleagues have been presenting on system identification and modeling, and Ram Krishna was introduced us. So this is an collaborative effort between different faculty, and we would like to explore problems in learning control evolution of network systems. So the tutorial, as Neerav, the slide is very familiar for those of you who were here yesterday. So yesterday we looked at, Neerav covered how do you model reaction systems, introduced the concept of stoichiometric matrix, a rate vector, the role of identifiability. He introduced, he also showed how you could, there are linear relationships between the different species that take part in concentration, and that is to be expected, right? And you have, let's say, A and B giving C. For every mole of A that is consumed, a mole of B is also consumed. So that should, we expect a certain linear relationship between the different species taking part in reactions. And therefore, even though there will be a large number of species that are taking part in reactions, there is a linear relationship between them. And it can be shown that these concentrations or the mole numbers, whatever, they lie in a lower dimensional subspace. And the extent domain is useful to capture that lower dimensional subspace. So it covered rate identifiability, that is in reaction systems. You collect, you typically measure indirectly or directly concentrations or mole numbers of different species, and you're interested in building kinetic models. And therefore, there are two things that we need to estimate or quantify: the rate of the reaction, and then these rates themselves are parameterized in terms of rate loss. So how do you estimate the parameters in these rate loss? In the interest of conserving bandwidth, let me just stop video. Today's lecture is going to focus on the parameter identifiability and the technical ways of ensuring identifiability. In some sense, it is very, again, you can use a lot of, even though the original systems are nonlinear, a lot of linear analysis can help us give in some insights. And some idea of Gauss elimination is really generalized to nonlinear polynomial systems, differential systems. If you're ready to take a leap of faith and make the parallel between Gauss elimination that we do for solving linear equations, and to do symbolic manipulation and elimination when we work with differential systems. So what is a priori identifiability? When we are dealing with dynamic systems and we collect data of the measured quantities, let's say, as I said, in reaction systems, directly or indirectly, we would measure concentrations or amounts of different materials or different species that are participating in the reaction. And we would like, let's say you have a hypothesized model, dynamic model for these. You are interested in identifying a unique model of the underlying system from data. And the uniqueness is important because if there were multiple models which could give rise to the same data, then you are in trouble. So the problem of identifying a unique model, that depends on three aspects. The first is completely dependent only on the model and the structure of the model and what measurements you have. So it is what we call a priori or model identifiability. It's a structural property of the system. It is in some sense a yes/no answer. Are the parameters identifiable or not? In this case, it's also it's done at a, as Neerav mentioned yesterday, it is done at a theoretical level, in the sense that we don't work with real data, but we work with the model of the system. We don't have the parameters of the system. We work with the model, the structure, and we assume that we know what we are going to measure. And in this case, again, we don't assume any measurement errors or what inputs are going to be used. So it's a concept, it's a structural problem that we're trying to, question that we're trying to answer. Second aspect of model identifiability is, because they are dynamic systems, it depends on the input. Now you could, there's a notion of persistently exciting or richness of the input in system identification. If your input does not perturb the relevant frequencies of interest, it's going to be difficult for you to build the dynamic. So that depends. Therefore, the problem of identifying the unique model depends on the input characteristics. And then finally, estimation method. Here, we are going to assume that we are not working with data. We are not working with noise. We're not working with uncertainties. It's a structural problem that we are interested in answering. Does there exist a unique model or unique one-to-one map between the model and the parameters being identified? And this is a simple question that we will be trying to answer. And this question, in this tutorial, we will specialize these to reaction systems. So I'll just motivate the intuition or how we build up this problem of answering this question. Let's have two reactions over here involving 5 species, and the reactions are occurring in what we call a constant volume batch reactor. So the species are A, B, C, D, and E. The first reaction, you can assume that 2 atoms or 2 molecules of A, they decompose to give B and C. This is, if you recall your high school chemistry, this is a reversible reaction, which means the reaction can go both. 2A can give you B and C, and B and C can also combine to give you back 2 molecules of A. So the net rate of this reaction, there's a forward reaction, and we assume this is called a mass action kinetics. Typically, in mass action kinetics, the rate is proportional to the speed, the concentration of number of atoms of the species that you have raised to the coefficient in the stoichiometric matrix. So in the forward reaction, the rate of the reaction will be K1 Ca square. The Ca denotes the concentration of A. And the backward reaction, because it's a mass action kinetics, B and C have to combine to give you A. So you can assume that the reaction rate depends on both the number of atoms of B and C which are there. So the net rate of the reaction is, there's a forward component K1 Ca square, and there's a backward component, or the reverse is minus K3 Cb times Cc. The second reaction involves 3 moles of B and A, giving you 1 mole of D and E each. The rate of this reaction, again, if you by mass action kinetics, it is proportional to A, and because B, there are 3 moles of B which are present over here, it is Cb power 3, Cbq. Now the stoichiometric matrix, there are 2 reactions. So R1, and therefore the stoichiometric matrix has 2 rows and 5 columns. The first column corresponds to A, the second column B, C, D, and E. If you recall from yesterday's discussion, the stoichiometric, the 1 entry of N will be the minus of the negative of the stoichiometric coefficient of A, which is occurring in the first reaction, so it is -2. B and C are products, so their stoichiometric coefficients will be positive, and therefore you see 1 and 1 because the reaction produces 1 atom of B and C. Second reaction, you take up A and 3 moles of B, so the coefficient of A is -1, coefficient of B is -3. There is no C which is participating in second reaction, so the 2, 3 element is 0. The 4th and the 5th elements of the second row are 1 and 1 respectively. Now you can write, now you can write the mole balance for the reactions. If you recall, dC by dt is N transpose R, or you just look at quick revision, intuition of how this reaction, how we write it. Think about this. A is being consumed in the first reaction, being produced in the backward reaction of the first reaction, and also being consumed in the second reaction. So dC by dt, you should expect a negative -2 K1 Ca square minus K2 Ca Cbq, because it is being consumed in the second reaction. It is also being produced. Sorry, there should not be a. Oh, there will be a 2 over here. Yeah, there will be a 2 over here because the the reaction, the forward reaction, the first reaction, and goes in the backward direction, it produces 2 moles of A. So you get 2 times K3 times CbCc. Likewise, Cb by dt, you would have, because it will be R1 minus 3 times R2, and that's what you get over here. K1 Ca square minus K3 CbCc minus 3 K2 Ca Cbq. Let's take D and E are the easiest. D and E are being produced only by the second reaction. So dC by dt and dd by dt and dE by dt will just be K2 Ca cube and Cbq. C is being produced in the first reaction only. So it is K1 Ca square minus K3 CbCc. So you can abstract this out, and you can verify that this can be written as N transpose R1 R2. N transpose is a 5 cross 2 matrix, and R1 and R2. You have the rate vector is a 2-dimensional rate vector. The first one is R1, the second is R2. So again, quickly you can look at this and verify that the 2 rows are independent. Therefore, the rank of the reaction, the 2 reactions are independent. if you recall definition of independent reactions, these two reactions are independent. Now, let us assume that of all the 5 species that are participating in the reaction, you measure only D and E. C and D. You measure only C and D. Now, again, even though there are 5 species, as I said, in this case, there are only 2 independent quantities, 2 extents. Everything lies really, even though there are 5 species, they're actually lying in a 2-dimensional subspace. There are linear relationships between all the 5 quantities. How do you derive that? Let's take the simplest one. We are measuring D and E, but we know that for every mole of D which is produced, 1 mole of E is also produced. So any change in D, the same amount has to be there seen in E. So that's where the last equation comes in. So if you start with CE0, if the initial conditions are all CA, CB, CC, CD, all indexed by 0, then any change in D is equal to the change in E, and that's what the last reaction tells you over here. Now, for B, for every 1 change in mole of C, there is a change in B by 1, and therefore that is CC minus CC0 that comes over here. Likewise, for every mole of E which is produced, 3 moles of B are taken away. So CB minus CB0, there are the change in B, it has 2 contributions. One because of the first reaction, and which is denoted by this over here. This is the change in the first reaction, and the second reaction, which is denoted by this term over minus 3 times CD minus CD. Now again, A, there are changes because of the 2 reactions. From the second reaction, for every mole of E which is produced, 1 mole of A is consumed. So that's what is shown over here. Any change in D, there is a negative of that is any production in E is a consumption of A, and that's why you see a minus over here. Likewise, any production of C, there is a consumption of A, and therefore you see a minus 2 into CC minus CCC. You could also derive this using the extent model. We'll come to that towards the end of this class, tutorial. So that what I was trying to say is, even though you had 5 differential equations, now I have been successful in expressing 3 of the concentrations in terms of the 2 measured concentrations. So you go and plug these back in the original equation over here. So you can write, remember, D in the CC, DC by DT, D by DT, depends on A, B. Likewise, E also depends on A and B. Sorry, C and E. So therefore, you need to write all the concentrations in terms of only the measured quantities, that is C and D. And when you do that, you get these 2 expressions over here. And everything else, once you are able to integrate this, if you know the initial conditions, you can integrate these 2 equations. You can get the future trajectories of C and D, and the few other values of A, B, and C can be obtained from this simple linear relationship. Now, you look at this. Now, since the right-hand side is only a polynomial, where is the nonlinearity? Nonlinearity is only in the concentration. There is no nonlinearity in the parameters. K1, K3 are appearing, or K2 are appearing only linearly. So you expand these terms out, and you collect the monomials of different types. So what kind of monomials will you get over here? You'll get a constant. You'll get CC, CD, quadratic terms, CC square, CC, CD, CD square. There'll be cubic terms because there's a cube over here which is taking, there's a cube. There'll be cubic terms which will come over here. Now, all these things will multiply the constant and you'll get cubic terms. So you'll get all kinds of, all the 4 cubic terms you'll get. CC cube, CD cube, CC square times CD, D square, C. And then likewise, there'll be 4th order terms. So you collect all the monomials together over here, and then they are all being multiplied by some linear functions of the parameters. And that's what I'm writing over here. So you write dC by dt in terms, collect all the monomials over here, and these are the linear functions of the parameters. Again, this I can write it as a matrix times x times theta, where theta is my set of parameters which I'm trying to estimate. In this case, they are K1, K2, and K3. Now I can do the same thing for CD. dc by d by dt, I can write the same thing, except I get a different matrix over here, x2. And then I get my parameters over here, theta1, there are three parameters, k1, k2, and k3. So I'm going to collect my two matrices, x1 and x2, and concatenate them one below the other. And let's say now I'm measuring the concentrations at different times. And again, once you assume that the concentrations are measured, now bear with me, assume that the derivatives are also there. Now you'll ask, how do you get the derivatives? What kind of, are you approximating them? Are you numerically differentiating them? Let's leave all that aside for a while. And then just assume that because concentrations are there, let us assume somehow, we are getting the functional form of the concentration. Therefore, you can do differentiation and get the derivatives also. So, and let's say this is available at times t1 to tn. I'm going to put the derivatives, concatenate them vertically one below the other. And I'll assume that I have some, this will I'll call my data matrix. The left hand side is my data matrix. Sorry, the output measurement matrix. And this matrix is over here, my data matrix. And this multiplies further x, where x was the coefficients of the parameters that are appearing, and then my theta over it, k1, k2, k3. Now you can think of, again, as I said, let's assume there are no errors. Now these equations have a solution clearly, because the same this physical process, chemical process gave rise to these measurements. So definitely there exists at least one solution for this. Because these concentrations have been obtained by integrating, or because let's assume the nature is really following this this reaction system, then obviously there exists at least one solution for this. Now, to ensure uniqueness of the solution, you have to ensure that the matrix, this data matrix times x, is full column rank. Now, of course, even though there are, that could be bilinear terms, cubic terms, and so on. Assume that, because of non-linearity, it's very unlikely that there would be a linear relationship between the columns of this data matrix. So the data matrix you can assume is full column rank. And therefore, the matrix which is multiplying, the pre-multiplying your vector of unknowns, now the rank of that will depend on the rank of x. What is x? X is basically containing the coefficients of your theta that are coming over here. So how do you get, let's say, the first one? Now, you think about this, there is going to be you expand these out, collect the coefficients of the polynomials and so on, and you will get a matrix X will look something like this. It's of course going to look much longer because it will have as many rows as the number of monomials which are there. So there will be the linear monomials correspond linear terms, constant linear, quadratic, cubic, and fourth order. So I don't need to in fact go all the way, because X, but the number of columns is only going to be 3 because there are only 3 parameters. So what I've done is I've only determined X partially over here, and then you can clearly see that X, there are many rows, but only 3 columns. So from this itself, it's very clear that the rank of the matrix is 3. All the 3 columns are, the 3 rows are independent. Therefore, the columns also are going to be independent. If 3 rows are independent, obviously the column rank is equal to the row rank. In this case, it is 3 rows are independent. So therefore, column rank is also 3. And therefore, this system of matrix equations, if you think about it in terms of linear, just assuming linear theory, standard least squares ideas or linear equations or determined equations, here you will get a unique solution. So at least this kind of gives you an intuition about how we are going to, what is the intuitive, even though the system is really non-linear and there are differential equations, the idea of doing some kind of linear analysis, helps us to anticipate what conditions that will be needed when you want to do the full-fledged theoretical analysis. Of course, here, as I said, there are certain hand-waving arguments that I used. I assume that somehow the concentration derivatives are available. The data matrix is full column rank and so on. But the intuition is, I hope the intuition is there that as long as there is enough, independent, there is some matrices is full column rank, or if there is some uniqueness of solutions, then the system can be said to be identified. Now, before I proceed, and then just take a short breather and see whether there are any questions or doubts about this. Okay, I don't see any comments, questions, concerns. So let me go to the formal definition of identifiability. So as you could see, the system of the equations are nonlinear. So you can write it in the familiar state space form. X dot is f of x u comma p, where x is the s-dimensional state vector. U is, there are r inputs. So R outputs, V inputs, and P parameters. We'll of course assume that F, G are sufficiently smooth and maybe Lipschitz continuous or differential. Moreover, for most if you want to apply the differential algebraic methods, you need to assume that F and G are rational or polynomial functions. Now, what the question is, if you give the structure of the model, and the parameters theta, which are it should be theta over here, not p, it should be theta. Are the parameters theta a priori identifiable from given the structure of this system over here? Now, let's call sigma theta as this nonlinear system over here. So when it is indexed by theta 1, it means I have put theta 1 as the set of parameters. If I index it by theta 2, it means I put theta 2 as my set of parameters. Now, the formal definition of identifiability is if you give theta 1, sigma theta 1, some set of parameters and a corresponding realization for the nonlinear system with that parameters, and a set of parameters, another corresponding nonlinear realization with theta 1 not equal to theta 2, if there exists at least one input u, such that these two realizations of this nonlinear system yield different outputs. Again, I'm sorry, it should be different outputs. Then the system is globally identified. If for finite set of parameters, all inputs result in the same output, the system is locally identified. I think this can also be extended to say countably finite, but let's keep it simple and straightforward and restrict to finite set of parameters. If for all theta, all inputs result in the same output, the system is unidentifiable, which means pretty much that means what this the second statement means, there are neighborhoods around a certain set of parameters for which different parameters will give you rise to the same input, same output. So that's why it is only locally identified. Now another way to think about this in terms of parameters is, rather than looking in terms of inputs and outputs, if the system sigma theta 1 and sigma theta 2 yield the same output for all inputs, the parameters theta 1 and theta 2 are indistinguishable. That also, I guess, it's just almost tautological, because if the system yields the same output for all inputs, the parameters cannot be distinguished from each other. Now, we can also define parameter identifiability in terms of this indistinguishability. If there exists at most a finite number of indistinguishable parameter values, the system is locally identifiable. If there exists an infinite number of different indistinguishable parameter values, the system is unidentifiable. So what is the approach that is used in the differential algebraic method? So what we do is we try to convert the original system of equations by differentiating them, doing symbolic manipulation and so on. And then recall, there are R outputs. So you should expect in some sense, R relationships between the inputs, outputs, the derivatives and so on. Because it could also be, in some pathological cases, it could also be lower than R. But let's say R outputs, and then the outputs are independent in some sense. You should expect that there are R relationships. It could be nonlinear. It could involve derivatives of inputs, outputs, and so on. And we want to get these. then what we do is we look at these polynomials. These are basically very similar, exactly what we got over here. So these are my polynomials that I've got over here. I've written everything in terms of two differential equations, which involve, in this case, on the left hand, it had only first order derivatives. It did not need any higher order derivatives, but we will see in some cases, you will indeed need higher order derivatives also. In this case, we are lucky that we could work only with first order derivatives, but in many cases, certain polynomial functions, rational functions, we may have to work with higher order derivatives. So what basically you're doing is, we're trying to eliminate the states from the nonlinear differential equation. We're trying to eliminate states. If you differentiate y's, you can hopefully, after a certain finite number of steps, you'll be able to eliminate the states, and you'll be able to get relationships only between inputs and outputs, and maybe some of including and maybe the derivatives. Then you look at the coefficients of those polynomials, which is called the exhaustive summary h of p, and then take any arbitrary value of p star, and we'll plug in these values. I'll show you these with examples. Plug in, evaluate these this exhaustive summary for that chosen arbitrary value of p star. If you get a unique solution to this system of nonlinear equations, then the system is globally identifiable. If you get multiple but finite number of distinct solutions, it is locally identifiable. If you get infinite number of solutions, it is unidentified. So this, there's a software, differential algebra for identifiability of systems, DAISY, brought out by colleagues from Italy. I think, unfortunately, I'll not be able to show you a demo today. Hopefully, my colleague Neerav will be able to show you a demo tomorrow. It's freely downloadable, and maybe I suggest that you download it, and before we come to maybe tomorrow's tutorial, it might not be a bad idea for you to download it, experiment with it. So what it does is, you give the nonlinear state space model. It applies what's called the Ritz algorithm to give you the characteristic equations, which basically, if there are R independent outputs, it gives you R relationships involving derivatives of the inputs and outputs. Then it uses Buchberger algorithm. Buchberger algorithm is basically just another way of finding out Grobner basis. Again, it is very similar in some sense to, basically it's a way of solving nonlinear polynomial equations symbolically. In a very crude manner, it is basically in some sense trying to do Gauss elimination, but with symbolic manipulation and polynomials. So I'll give you I'll walk you through with an example. This system involves rational functions. So there are three parameters. It's a very famous biochemical system. Two states and one measurement, y. Three parameters, Vmax, Km, and P1. So these are the three parameters which we want to estimate, which we want to see whether we can estimate them from measurements of y. Time course measurements of y. So we write this equation over here. Again, recall these are the two differential equations and one measurement equation. So we need to first rearrange your rank the variables. So the ranking scheme is usually inputs are lower than outputs, then the states are the highest, and the derivatives of states even higher than that. So the ranking is basically, it's a lexicographic ordering of the variables. Inputs are always going to have lower rank than the outputs, which will have lower rank than derivatives of the inputs and higher derivatives of the inputs. Again, which will because they are already lower than inputs are lower than outputs. Derivatives of outputs will also be lower than derivatives of inputs will be lower than derivatives of outputs, and states are the biggest guys. And derivatives of states even bigger than that. So this is my ranking scheme which I've chosen over here. So we first, because it's rational, we take the clear fractions. We take the numerator to the right, clear it out by multiplying it accordingly. Clear the fractions, and you'll get three equations. Two of them will involve derivatives. Third will be a simple linear equation over here. So that same two compartmental model I've converted into polynomial form. What I've done is the first equation I multiplied by Km plus x1 on both sides. So I get this over here. The second equation also I multiplied Km plus x1. I get this. The third equation was minus x2 plus 5. Now I'm going to rank. This is my ranking scheme that I've chosen. Now, for every equation, which is the highest guy over here? let's say take the third equation over here. The highest guy is x2. So the leader of this equation is x2 over here. Now, for the second, and then I will rearrange this in decreasing order. Remember, x2 is higher, x in ascending order, x2. The second, look at this equation over here. The first equation over here, x1 dot into km plus x1 plus this, which is the variable which has the highest ranking according to the scheme. The first equation. Let's go first one by one. The first equation, which is the one which has the highest ranking, which is a variable that has the highest ranking. The first equation. Because of very few people, I can make it easily interactive. The first equation. This is a ranking scheme. Inputs smaller than outputs, smaller than states, and the highest is the derivatives of states. So the first equation, which is a variable which has highest ranking, or label which has the highest ranking.
Derivative of x1.
Derivative of x1, right? So that I have written over here, that comes over here. The second equation, which is a variable that has the highest ranking.
Derivative of x2, sir.
Derivative of x2. The third equation, the variable that has highest ranking is x2. Now between x2, x1 dot and x2 dot, this is the ascending order. x2 is lowest rank, x1 dot is highest rank, and x2 dot is highest rank. So I rearrange these equations also in this form. I put the lowest ranked equation over here as minus x2 plus y, and the leader is x2, which is basically the variable which has, or label which has the highest rank. So the first equation is minus x2 plus y, the leader is x2. The second equation is this guy over here, the leader is x1 dot. The third equation is this one, where the leader is x2 dot. Now I'm looking for a specific structure. Like we call Gauss elimination, we are looking for a specific diagonal structure. I don't want, what I don't want is every polynomial is compared with the previous ones. If it is of equal or higher rank, then it has to be reduced. You have to reduce with the preceding one. Exactly like Gauss elimination, there are non-zeros, we try to make zeros over there, right? Try to get a tri-diagonal system. So this third equation is compared to the first one. It contains the leader of the first polynomial. The third equation, the leader of the first polynomial is polynomial is x2. It contains that. So I'm going to try to eliminate that, and it's very easy to eliminate, right? Because how can I eliminate it easily? x2 is equal to y, right? Because minus x2 plus y. So this elimination is very easy. So I can eliminate x2 from this third equation over here. So it's basically I'm trying to eliminate x2 from the third equation. x2 can be replaced by y. And then now after doing this, the ranking also changes. Remember, now y is the lowest. Output is smaller than states, which is smaller than derivatives. So now the first equation, the ranking now changes. Because initially it was x2 dot was there, but x2 is now replaced by y. So I get y dot into this. So here the leader is x1. The second, the ranking of the equations also changes. The leader of the second equation is x2. The leader of the third equation is x1. The second polynomial is reduced with respect to the first one because it does not contain the leader of the first equation. So minus x2 plus y does not contain the leader of the first equation, so that is fine. So in some sense, some diagonalization has already been achieved with that. Now only the third guy still has the leader of, it has x1. So I have to eliminate x1, and interest of time, x1 can be eliminated by enough number of differentiations and algebra eliminations. And finally, you will end up getting this giant nonlinear equation over here. It goes through 3 rows. And because it goes through 3 rows, I have to choose a smaller font size for this. But what I want you to notice is there's a structure for that. The first equation there is no state appearing at all. It has only u, y, and y dot and y double dot. The second one has only y and x1. The third has only y and, in this case, it doesn't have any x2, it has only y and x2. So there is some kind of a diagonal relationship which I've got. The first equation, in this case, there's only one measurement. Therefore, there's only one nonlinear differential equation relating the inputs, outputs, and the derivatives of those. And that happens to be this equation over here. Of course, it is symbolic because it becomes because of polynomial manipulation, symbolic algebra is involved. You end up getting from simple equations, simple differential equations, only 2 or 3 terms, at the expense expense of having to eliminate the states. The price that we pay is we get a very large differential equation. It involves second derivative of y cube, y dot cube, and y dot square, and so on. Now, you take all the derivatives of all the distinct terms that monomials. Now in this case, monomials will also be generalized to involve derivatives of y, y dot, and so on. You take all of these coefficients of y dot. You'll find that in this case, Km Vmax is common, so you can divide the whole thing by 1 Km Vmax. You look at this, Km Vmax multiplies everything, so you can divide everything by Km Vmax. So you collect all the distinct coefficients of everything. You get that these are the only forms over here. Km Vmax minus P1 Vmax, and so on, minus P1 Vmax, and so on. So that's the only thing, only distinct terms that you get. Now, I have arbitrarily chosen with some value, P1 equal to 28, Vmax equal to 15, Km equal to 14. Now, I'm going to therefore solve, and then I'll put these values over here in this one. How many equations do I have? 1, 2, 3, 4, 5, 6, 8, 9, 10, 11 equations. I have 11 equations, these nonlinear equations. Because Km Vmax, I know the values of Km and Vmax over here. Km is 14 and Vmax is 15. So Km Vmax plus 210 is equal to 0, or minus 210 equal to 0. So P1 equal to 28, Vmax equal to 15. These are obviously straightforward, but you also have nonlinear equations because there is a P1 square. So P1 square equal to 784, and so on. So now, if I solve these nonlinear equations using Grobner basis, the Buchberger algorithm to solve nonlinear equations, nonlinear polynomial equations, you get what's called the Grobner basis. And in this case, there is a unique solution. So what that means is, even though I have randomly chosen, of course, this is a generic test because I have randomly chosen the values of P1, 28, P1 equal to 28, Vmax equal to 15, Km equal to 14. I've randomly chosen these values of the parameters, and then I plugged it in these nonlinear equations. I get a unique solution. So it's with very high probability, it is true that the system is globally identified. Again, I'll just maybe pause for a minute if there is any question. So the elimination algorithm, even though I've glossed over it, it is in some sense a generalization of the Euclidean division algorithm for polynomials or for integers. The polynomials are like integers in some sense. You can multiply, you can add, you can subtract, but you can't divide. Because in the moment you divide, you may not get polynomials, and therefore they form rings. So no questions, then I can proceed. So now we apply this. We use the same DAISY approach to this system over here. And then, intuitively, okay, let me ask you this question before we go into this. If I measure, there are two independent reactions, there are two rates, right? So you need to measure two things. That's the intuition. We need to measure because there are two rates. Neerav mentioned this yesterday about being able to estimate rates. So there should be at least two things that you need to measure over here to get the rates. Now, it's not just enough if you are able to measure the rates, you also need to estimate the parameters K1, K2, and K3. Now, let me ask you this question. If I measure D and E alone, do you think the system is identifiable?
I think no.
Yeah, the system is not identifiable. In fact, because both, in some sense, they're redundant, right? Every mole of D and E are participating in exactly the same reaction. So if you, or equivalently, as Neerav mentioned, you will have the stoichiometric matrix corresponding to E and D is this block over here, 0, 0, 1, 1. It's the columns are dependent. Or equivalently, think about this. Whatever information D is giving, the same information E is also giving. So you don't get any extra information, even though you are measuring two quantities. So if you run DAISY for different combinations of measurements, you can run DAISY. The state equations X dot is the same. What will change with different measurements is your Y equal to HX. The measurement equation will change because in one case, depending on what you measure, there are different possibilities. And there are 5 species. So there are 5C. So there are 10 possibilities, right? 5C2, 10 possibilities of measurements are there. It turns out, as we saw over here, if you measure D and E, then system is non-identifiable, and D and E over here, the system is non-identifiable. It's a symmetric matrix, of course, so you can only look, it's enough to look at the lower or the upper triangular part. For every other combination A and B over here, for instance, the system DAISY, software DAISY returns that it is globally identified. Unfortunately, even though we had seen, right, intuitively that D and if you measure D and C and D, the system was identifiable. I hope you are, none of you are going to contest that. But because this matrix was a full column rank, we kind of expect that with C and D, the system should be globally identifiable. But unfortunately, even for this seemingly small system, DAISY is not able to give an answer. NR means no, DAISY was not able to give an answer, definitive answer, whether it is identifiable or not. Basically, it could not. Even though these differential algebraic methods are bound to converge in finite number of time, but what is finite could be extremely large. It could be an exponentially large number of operations may needed, and therefore, in reasonable time, DAISY could not return an answer. Even though we know and we expect also that with D and E, you should be able to estimate all the parameters. So this is one limitation of the standard techniques of using differential algebra. Standard differential algebra. Now, this can be elevated by, rather than looking at it in the 5-dimensional concentration domain, you can look at it in the system of the model extents can be in the lower dimensional domain, in the extents. As far as DAISY is concerned, you need to give 5 differential equations and 2 measurements. But we know that the system can be described in the model, in the extent domain, with fewer number of state variables. Only in this case, 2 variables are enough. For two variables are enough over here, the state variables, and with 2 measurements, the entire number of states is only 2 over here. The entire state space dimensionality can be reduced significantly. And DAISY does not know this, unfortunately. DAISY is not able to discover these linear relationships. It just treats them as arbitrary polynomials. The entire system is arbitrary polynomials. If some intelligence were built in DAISY, it may have identified that there exist linear relationships between the A's, B's, C's. A, B, and C can be written in terms of D and E. That unfortunately does not recognize, even though there are these algorithms to do symbolic manipulation. And that's where this extent domain, rewriting the equations in extent domain is helpful, because you write this equation in extent domain and you get the input output map. Lo and behold, you get the input output map over. Right, and this is the input output map. Okay, this involves y1 and y2, but you can again do elimination. You can eliminate y1 dot from the first equation and y2 dot from the second equation. You will get 2 equations involving only derivatives of inputs, outputs, and the output variables. So you get the input output map is readily obtained if you were to do using state variable, using the extent domain. However, even this was not possible for DAISY for a simple reaction when the C and D were measured. And in this case, again, you can convince yourself, you put in these parameters values over here. This is linear, in fact. The coefficients of y1 square is 7k1. The coefficients of y2, y1, y2 cube is 7k2. The coefficient of, say, y2 times y3 is minus 3k3. You'll see that the equations will have unique solution. So it has globally identified. And this is what we got for the case when this is when A and B are measured. I'm sorry. This is when A and B are measured. I'm sorry. This is when A and B are measured. When C and D are measured, this is the kind of differential equation that we are expecting, which DAISY could not obtain even after a reasonable amount of time. And this is exactly what we are interested in. And what we had got by, I started off the talk today by taking recourse to some very simple chemical laws, but the same can be generalized in this theorem over here. The theorem says that if the measurements are chosen such that the stoichiometric matrix is partitioned into two parts, the first corresponding to measured species, second corresponding to the unmeasured species, and the measured part is full rank, then the characteristic set can be given by just the simple equation over here. And once you can again get rid of the the coefficients of NM transpose pseudo inverse over here by taking again pseudo inverse of this matrix, you will be able to get y dot. Again, sorry, this should be theta. I mean, I'll make sure when the slides are, if at all we share the slides, this should be theta. So you will be able to get everything in terms of only your measured variables. Whereas DAISY is not able to give you this input-output map in terms of the measured variables, even for a seemingly simple system of equations. We get the same, on the matrix over here, which is full rank, and it is the system again. The system is linear, globally identified. So just to conclude, this is how DAISY works. I mean, this is standard differential algebraic method. You get the state space equations x dot is f of x, y equal to g. You eliminate all the state variables and you get a set of polynomial differential equations, which could involve higher derivatives of inputs and outputs. You collect the coefficients of the different monomials. You apply Buchberger algorithm to see whether the nonlinear equations, the polynomial equations that you get, have a unique solution. For even for modest reaction networks, this fails. In fact, our idea can be applied on very large networks. We tried it with 14 reactions, 20 species, 12 independent reactions. There are 14 reactions, 2 of them are dependent, 12 independent reactions and 20 species. The DAISY has no, standard methods will have no hope for doing this. We rewrite it in the extent domain, and it just, in fact, not it just in this case, if the reactions are follow mass action kinetics, it just boils down to a simple rank test. Even you don't need to do Buchberger algorithm if the reactions follow mass action kinetics. If they are rational functions, you may have to still do Buchberger algorithm. But even that, we have a hypothesis which is partially proven that for certain reactions, again, linear rank tests are sufficient to determine global identifiability of parameters. Another disadvantage of the limitation of the conventional differential algebraic approaches, these work only with rational or polynomial functions. Tomorrow we will see systems where where there is a change in temperature, and when there is change in temperature, the reaction rates double. Again, if you reaction rates change. If you recall your high school chemistry, for every 10-degree change in temperature, we expect the reaction rate to double. So there exists a certain, and that clearly shows exponential growth. So once you have exponentials, it's difficult to use, or pretty much impossible to use, traditional methods which work only for polynomial or rational functions. So we have come up with ways. It should not be too hard to guess what we will be doing tomorrow. I'd like you to think about what, of course, the paper is also there, so you can look at the paper. It came in Automatica about a couple of years back. And if you're, if you're really keen, you can look up that paper. Just search for Narasimhan Bhatt at Automatica, you'll find the paper. Or maybe I can open it up here also. With this, I'll stop, and then we have about 5 minutes for discussion, inputs, comments, feedback. this is the link for the non-rational part, and for the some of this that we presented today was presented in the society conference in 2018. Any This is the second link is the one to the conference presentation proceedings about how can you use, where you formally prove that writing the equations in state space form, it's very easy to get the input output form, input output characteristics. So there are no further questions.
I think there are not many questions.
So we can formally close for tonight.
Yeah, I think we can. So tomorrow at the same time, we'll discuss non-rational functions and briefly the DAISY, how to use DAISY. And also there is a new software which has been come, which claims that it's better than DAISY. We'll just introduce that also. It can be used, you can see. So we'll only discuss DAISY, but I'll just let you know the other software also, which are available for identifiabilities. Then thanks, Caesar, for giving a talk. And we'll close the session today then.
Yes.
Thank you, everyone. Have a nice evening, and thanks for attending talk. Please come tomorrow. We'll conclude talk and show you some hands-on tools which actually use some of these theories to to test identifiability. Thank you very much. Have a nice evening.